So in our previous lecture, we discussed about various pin configuration of ADC and some important terms like step size and number of steps and how to find out the digital output for particular analog value. So all these things we have discussed. Now today we are going to discuss one example of ADC interfacing. But before coming to that interfacing example of ADC, we will discuss one instruction which we will use in our this interfacing example. And the instruction is compare instruction. It is used for compare two numbers. The instruction format, the instruction mnemonic is CJNE. This means compare jump not equal. So this instruction will compare two numbers. We will call one first number as destination and second number as source. So it will compare two numbers and after the comparison, depending upon two values, destination value and the source value, if these values are not equal, then program sequence will jump to a particular label. So the syntax of this instruction is compare jump not equal, destination, comma, source, comma, relative address. Relative address. So here in this instruction, the content of destination and content of source will be compared. And if both the numbers are not equal, then the sequence of program will go to the relative address. Then the jump will take place. Otherwise, if both the numbers at destination and source are equal, then sequence of program will not go to the relative address. It will not jump. And in this case, whatever instructions we have written after CJNE, those instructions will be executed. So, suppose this is relative address. At this address we have written certain instructions. Right? Here we have written instruction. So certain instruction we have written here. So these set of instructions will be executed if destination is equal to source, and these set of instructions will be executed if destination is not equal to source, because the instruction is compare jump not equal. If the value of destination and source are not equal, then jump. So if they are not equal, then jump to relative address. And relative address is here. So these set of instructions we will execute when destination and source value are not equal. But if the values are equal, destination and source contents are equal, then sequence will not go to the relative address. This program will come out from the loop and these set of instructions will be executed. So these set of instructions will be executed if destination and source are equal. So now in this instruction, basically what this instruction will do, it will subtract the value of source from destination. Basically this subtraction operation will be performed. and if destination is greater than source, right? Example, suppose we take here our destination is 09 and source is 02H. Suppose these are the numbers and the destination value is 09H and source value is 02H. And when this instruction is executed, then internally controller what it will do? It will subtract 2 from 9. So we know during this subtraction, since destination is greater, so no borrow is required for the subtraction. So if no borrow is required, then in this case, carry flag will 0. While discussing about the PSW of 8051, we discussed that there is a carry flag, and the purpose of carry flag is it indicates whether carry is generated after addition or borrow is required during subtraction. So basically carry flag is used for borrow, for subtraction and addition both. So in this case, while subtraction, since no borrow is required because our destination is greater than the source, so carry flag will remain 0. Then second condition will be if destination is less than source. So for example, our destination is now suppose 02H and source is 09H. So when in this case it is 02H and this is 09H. So when this instruction is executed, then internally controller, what controller will do? It will subtract 09 from 02. And in this case, when we are subtracting 09 from 02, then obviously since this number destination is smaller than the source, so during the subtraction one borrow is required. And if borrow is required, then your carry flag will set. Then carry flag will set. So now when this instruction is executed, then there are two probabilities. First probability is destination is equal to source. This is the first probability. And second probability is destination is not equal to source. So if first this is the case, when destination is equal to source, then when this instruction is executed and destination is equal to source, then according to this instruction, compare jump not equal. Sequence will go to relative address when the source and destination are not equal, means here, relative address. Sequence of program will come to this place when destination is not equal to source, and here sequence of program will come for the when destination is equal to source. So now we will see the second case when the destination and source are not equal and this instruction is executed. Then the program sequence will come to this relative address. Now here, for the second case, again now there are two probabilities are there. One, destination is greater than source, and second, destination is less than source. Because after execution of this instruction, when the destination and source are not equal, then the sequence of program will come to the relative address, but when program sequence will come here, at this time we are not sure whether our destination is greater than source or destination is less than source. But obviously one thing is clear, when controller will come to this relative address, one thing is clear, that destination and source are not equal. Now whether destination is greater or source is greater, to find out this, again we have to use some instruction here to find out, right? So for this we can use instruction, here we can use instruction jump carry or jump no carry. Any one of the instruction we can use. Suppose we are using instruction, we are using instruction jump no carry, right? We are using this instruction. And let us assume our destination was greater than source, means the values were 09H and 02H. Destination was greater than source. So what will happen? When destination was greater than source, this was the case, then after execution of this instruction, your carry flag will be 0. So if we check here carry flag, we write the instruction jump no carry. D is greater than source. The meaning is this: when no carry is generated, then again I will transfer the sequence of my program to another level, DGS, means destination is greater than source at this level. So here we have written we can write few instructions which will be executed when our destination is greater than source. Now we will see if the case was second, means suppose our destination was smaller than source, like for example destination was 02 and source was 09H. So when this instruction is executed CJNE, at that time obviously destination and source are not equal. Due to this, program sequence will go to the relative address, it will come here, right? Now here we have written instruction jump no carry. If carry is 0, then go to this place. But in this case what will happen? This is case 2, destination is less than source. So in this case carry will set. So now jump no carry. This instruction basically will not jump to DGS because carry is set, and we have to jump to this level only when the carry is not set. So now program sequence will not jump. So it will come out from the loop and these set of instructions will be executed. So these set of instructions will be executed if destination is less than source. So in this way we can conclude whether our destination is greater than source or source is greater than destination. But with this instruction, one thing will be clear immediately, and that is whether destination and source are equal or not. If the destination and source are equal, if they are equal, then these set of instructions will be executed. Because if they are equal, then program sequence will not jump to relative address. But if destination and source are not equal, then we have to confirm whether destination is greater than source or source is greater than destination. For that, we can use JNC or we can use GC. Any of this instruction we can use. So this is about the compare jump not equal instruction, and this instruction has following forms. The source and destination can be written in following ways. CJNE, compare jump not equal, A, comma, RN, comma, at the rate, RI, comma, hash, data, comma, relative this is our destination number and this is our source. So here source is an immediate data. So that data will be compared with either A or any value of the register or we can use here register indirect addressing also. So basically there are three formats of this instruction. The format are like this. First CJNE A comma hash data comma relative address. So in this case A will be compared with immediate data. For example, we will see one example. Suppose we have written this instruction move A comma hash 09D. So with this instruction what will happen? A will become 09. 09 value will be loaded in B. And after this we have written instruction CJNE A comma hash 04H and for the relative address we have written a label ahead. Like this. So now with this instruction what will happen? The content of A will be compared with 04. This is a data now. So in A we have 09. So basically what is happening now? 09 and 04 are compared. And if these numbers are not equal, then go to label ahead. And if the numbers are equal, then don't go to the ahead label. Execute the instructions written after CJNE. So now in this case, here this is ahead label. So now sequence of program will come to this place. Since the value of A is 9 and value of it is compared with 04. This is our source. This is our destination. Now whether the value of A is greater than 4 or the value of A is less than 4, that we will find out here by using instruction JC or JNC. So this is the one form. And the second form CJNE. In place of A we can use RN comma data relative address. So here this destination can be R0, R1, R2 up to R7, any of the register. So now in this case, suppose if we write the instruction CJNE R3 comma hash 24H comma ahead. So now what will happen? The content of R3 register. So whatever value is stored at R3 register, that will be compared with this data 24. And if both the numbers are not equal, then go to label ahead. Otherwise, if both the numbers are equal, then don't go to ahead. Come out from the loop and execute the next instruction written after CJNE. So this is the second form. And the third form can be in place, in the destination we can use at the rate symbol. For example, CJNE at the rate R0 comma hash data relative address. So now our destination data, its address is specified by R0. So whatever is the value of R0, that will point the memory address, the RAM location, and whatever is stored at that location, that value will be compared with the immediate data. So this is one form. In this form there are basically three different formats, and there is another form of CJNE instruction. CJNE A comma direct address, relative address. So here the content of A will be compared with your source data, and the address of source data is given with the instruction. For example, CJNE A comma, if we write 30H and ahead, this is relative address. So now here what will happen? The content of A register will be compared with the content whose address is 30H. So now we already know that in our RAM, internal RAM in 8051, addresses are from 00H to 7FH, right? Somewhere you will find this address 30H. So at this address, whatever data is stored there, whatever data 8-bit number is stored there, so that number will be compared with the content of A register. And depending upon the values, whether A is greater than this content or whatever is the value, program sequence will jump to label ahead or it will come out from the loop. Now in this particular instruction, we know that from 00 to 7F, this is the address of internal RAM. And after this, 80H to FFH, these are the addresses of special function register. So here there is one special address for port 0, port 1, port 2 and port 3. So we can use that address also here. If we use that address, suppose here in place of 30H we have written the address of port 0, right? So what is the address of port 0? That you will find out from the books or from the manual. So in this case what will happen? Suppose this is your microcontroller. In microcontroller this is our port 0. So this is our port 0. And this is your input port. So now with this instruction what will happen? The content of A will be compared with the 8-bit value of this port, right? 8-bit value of this port, it will compare with that value. So we can use this port address also with this instruction. Only thing is here you have to mention the address of the port, but it is difficult to remember all the addresses, right, of a special function register. That's why user can use the name of the port while writing a program. After that, when you compile this code, then automatically what is the address of port 0, that will be calculated by your assembler or compiler, and that this P0 will be replaced by your that address. But you can use these names P0, P1, P2, P3, the port name, right? Okay. So in this way we have just discussed about compare instruction, and this instruction will be used when we are performing certain operation on ADC. Now suppose there is one application and our application is like this. Suppose there is one ADC 804. Now in this ADC, this is V in plus and V in minus is connected to ground. V reference by 2 is open, and this is CS bar used to select this chip, and these are analog ground, digital ground, both are connected to ground, and CLK in a clock of suppose 606 kilohertz is applied to CLK in. Now CLK R is open. Here we have connected plus 5 volt. This is the 8-bit data line of ADC, D7 to D0. This is our start of conversion pin. This is end of conversion pin, and this is read bar to latch the value in D7 to D0 pin, right? I think all the pins we have mentioned: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 and 9, 8 and 19 and 1, 20. Okay. Now what we will do, here we have connected one temperature sensor, right? So there is an IC LM35, right? This is a 3-pin IC, and it is basically a temperature sensor. So this is an IC having 3 pins, pin number 1, 2, 3. So pin number 1 is connected to VCC, we connected to plus 5 volt. Pin number 3 is connected to ground, and pin number 2 is your output, right? So depending upon the temperature, this LM35 IC will generate analog output. It will generate analog output depending upon the temperature. So that it can sense, LM35 can sense the temperature in the range of minus 55 degrees Celsius to plus 150 degrees Celsius. In this range it can sense the temperature, and with the resolution is, with each degree rise in temperature it will generate 10 millivolt, right? So for each degree Celsius it generates 10 millivolt. Now for example, if the temperature is 0 degrees Celsius, in that case output voltage. In that case output voltage is 0 volt. But if the temperature is 1 degree Celsius, then this IC here at the analog output, here at this pin, you will find a voltage 10 millivolt. If the temperature is 2 degrees Celsius, then we will get 20 millivolt. Like this, if the temperature is suppose 33 degrees Celsius, then we will get 330 millivolt. So in this way, this IC LM35 will generate an analog output voltage depending upon the temperature. So what we will do, we will connect that LM35 here. So we will connect in this way. This is plus 5 volt, this is ground, and this is our output pin, right? This output pin we have connected to V in. So now what will happen? Depending upon the temperature, and this particular arrangement we have placed inside one room. So the room temperature, depending upon the current room temperature, one output voltage will be generated. And that output voltage is connected to V in plus of this ADC. So this ADC will convert that analog voltage in digital form. And now here we will connect the microcontroller. We will connect here 8051 microcontroller, right? So this 8-bit data line I will connect to 8-bit of our port 1. And start of conversion pin I will connect to a pin number port 2, pin number 0. End of conversion pin of ADC I will connect to port 2, pin number 1. And read bar I will connect to port 2, pin number 2. Now I will connect 3 LEDs at the output side, right? Suppose this is red LED, this is yellow LED, and this is green LED. There are 3 LEDs. Here we have connected plus 5 volt. These LEDs, red LED, we have connected at pin port 3, pin number 0, yellow at port 3, pin number 1, and green at port 3, pin number 2. In this way we have made the connections. Now our aim is now if room temperature is greater than reference temperature, right? We will set some reference temperature. Let us assume our reference temperature is at 29, or we will take it 30 degrees Celsius. If it is 30 degrees Celsius is the reference temperature. If this is the condition, this is the condition number 1. If this is the condition, if our room temperature is greater than the reference temperature, then we will on the red LED to indicate some severe condition like that. So in this, on red LED. The second case, if room temperature is equal to reference temperature, that is 30 degrees Celsius, then we will on yellow LED, right, to indicate that okay, it is just equal to the reference temperature. And the third condition is if room temperature is less than reference temperature, that is 30 degrees Celsius, then on green LED, right? And we will sample this after some delay, right? For example, Suppose we sense the temperature. If the temperature, room temperature is greater than the reference temperature, then we will make red LED on, and yellow and green will remain off, and it will remain on for some period, right, for some duration, like 5 seconds, 1 second or 3 seconds, right. So we will not just calculate the exact delay, but only in our program we will give some delay so that this LED will remain on for certain time. So sample this after some delay. Okay, for some time the LED will remain like this, and after this again our controller will sense the room temperature, right. Again, depending on the temperature, some particular LED will glow. Again, after certain time, again it will sense the temperature, right. So this is the application. Now in this application, we have to just compare two values, right. We have to compare two values. For that we can use this instruction, compare jump not equal, and in A we can store our room temperature, and it will be compared with our reference temperature. It will be compared with our reference temperature. So our reference temperature is 30 degrees Celsius. So if the reference temperature is 30 degrees Celsius, then in this instruction, what value we should use here for the 30 degrees Celsius? So that value we have to calculate, right? Because for the 30 degrees Celsius, what digital output will be generated by this ADC, that we have to calculate. So as per this diagram, since V reference by 2 is open, since V reference by 2 is open, therefore V in range is 0 volt to 5 volt. This is the range. Before this range, we will find first step size. Step size, in last lecture we already calculated that it is maximum allowed input voltage divided by 256, right? So from that we already calculated it is 19.5 millivolt is the step size. Now for 30 degrees Celsius, V in, what analog value will be received at this pin? So for 30 degrees Celsius, this LM35 will generate 300 millivolt. For this it is V in is 300 millivolt. Now what is the digital output equivalent to 300 millivolt? So that we have to calculate. So for that we will use the formula, digital output is V in divided by step size. So here V in is 300 millivolt divided by step size is 19.5 millivolt. So we find out this value. Divided by 19.5. This is 15.38 in decimal. We convert it in round figure, so it will be 15D. And in hexadecimal it is, now we write it in 8-bit binary form. So in 8-bit binary, this 15 is 0 0 0 0 8 4 2 1, right? This is the equivalent 8-bit number of 15D. In hexadecimal it is 0FH. So for our this particular interfacing case, for 30 degrees Celsius, different temperature, we will get a value 15D or 15D or 0FH, right? So we will compare the room temperature with this value 0F. Now we have done the calculation. Now we will write the program to perform this operation. So for this calculation, I will write this value here so that I can get the space. So here, okay. The step size is 19.5 millivolt and okay. For 30 degrees Celsius, reference value is 0FH or 15D. So we will write our program from org 0000H. So first thing what you do, you see in this 8051 microcontroller, if there are any pins which we are using as an input pin, then make these pin as an input. So here port 1 is acting as an input port. So make this as an input port. For this we will write the instruction move P1, #0FF. You have to send once to these pins of this port, then it will become input port. So why we have written this instruction? So comment I am writing after semicolon, make P1 input. Now start of conversion, this is output pin, end of conversion is an input pin and read bar is a output pin. So this pin also we have to make input. So for this we will write instruction set B P2.1. So why we are making this? Making EOC input. Basically EOC end of conversion is the output for ADC, but it is acting as an input because we have to read the value of end of conversion. We have to read this value whether it is 1 or 0, because whenever its value will become 0, it indicates us that conversion of analog to digital has been completed. That's why this pin is input for EOC input. Okay. Then now after this, to start the conversion, what we have to do? To start the conversion, see by default we know that all the pins are output and you will get a high value, right? So here you are getting a high value. So to start the conversion, what we have to do? To start the conversion, for this start of conversion, a low to high pulse has to be generated, right? This low to high pulse has to be generated, low to high, then only the conversion of analog signal into digital will start. So by default this pin is high. So first we will make this pin 0 and after this we will make this pin 1. So what will happen? 0 to 1 pulse will be generated. For this CLR P 2.0 means SOC is equal to 0, and then set B P 2.0. So SOC low to high pulse has been generated. Right? Now the conversion process has been started, and once the conversion process will start, then we have to check this pin, because by default this pin here it is high, here it is high, right? This is high value. So what I will write instruction, jump bit P 2.1 here. So if this pin is 1, again come to same place, again you check this pin. So it is high, continuously controller will check this pin continuously. And the moment our conversion from analog to this digital completes, this pin will go low for a small duration, again it will come back to the high position. So the moment this pin will go low, so here this pin will become low, then what will happen? This instruction will not, it will execute it, but it will not go to the level here, because now it is 0. It is 0 means jump bit to here. Program sequence will come to this level only if this pin is 1, but now it is 0. Since it is 0, program will come out from the loop and we are here. So we are here now, we have to read the value of this ADC, right? So this value is inside the latch, that value has to be come over to this data line. For that there is a read bar. So here what we have to do, a high to low pulse we have to generate, right? So this is a output pin by default it is high. So simply we have to clear this pin. If you make this pin 0, then a low pulse will be generated. So here we will write CLR P 2.2. So with this read low to high pulse, right? Low to high pulse has been generated. Sorry, high to low. High to low. Because by default its value is this is output pin and by default it is high. And with the help of CLR P 2.2 we have made this pin low. So it is high to low pulse. And now it is high to low pulse has been generated. Now we can read the value of these data lines and we can bring this inside this controller through this port 1, and we will store that value 8-bit digital value in A register. So for this I will write the instruction move A, P1. So by this temperature equivalent digital value in A register. And now for the next round of operation, we again make this pin high. So that again we have to make it clear. So for this we will write set B P 2.2, right? For next reading. Okay. So now up to this point, whatever is the decimal digital value of current room temperature equivalent digital value, that value is inside A register of this microcontroller. Now once it is inside our microcontroller, now we can check whether that value is greater than or less than or equal to our reference value. So for this we will write the subroutine for that at some place. So L call compare. I will send the sequence of my program to somewhere where we have written the instructions for compare. This and this org 0050H, right? So here we have written the logic for verification of this. And after the verification, certain LED will glow, and finally program will come back to this point. And once it will come back to this point, then again we will repeat the process. So here S jump, repeat, and repeat will be from here. Repeat will be from here. Now for the comparison, we will write the instructions here for the comparison. So for this we will simply write the instruction: compare jump not equal A, comma, hash. In A we are having the room temperature, sensed room temperature, and it will compare with the reference temperature. Reference temperature is 30 degrees Celsius, and for the 30 degrees Celsius, for this particular interfacing, we will have a value 0FH. So it will be compared with 0FH. And if both the values are not equal, then go to further underscore compare. Right? So we will come to this place. If both room temperature and reference temperature are not equal, then we will come to this place. Otherwise, if both are equal, then we will come to this place. Otherwise, we have to further compare and we have to further check whether the reference temperature is more or room temperature is more. Okay, so we will write here further check, not compare. Already we have done the comparison, so further check. Actually, if we write further compare also, then also no problem, because in the label whatever we want we can use, we can write, right? But it is always advisable that we shall use the labels which signifies the particular meaning of our program. Further check. Now here I will use instruction jump no carry. Okay. So first we will see here these whatever instructions I will write here. These instructions will be executed if A is equal to 0F, right? So if A is equal to 0F, in A we have room temperature. Okay, so we can write the comment here itself so that we can understand with the code. If A, that is room temperature, is equal to reference temperature. Reference. If this is the condition, right? Then what we have to do? This is. If the room temperature is equal to reference temperature, make yellow LED on. So yellow on, right? Red off. So first we will make the red off. For this, set B P 3.0. This will make red off. Then CLR P 3.1. It will make yellow on. We will clear this pin. This pin we will make it 0. If it is 0, then this LED will glow, right? And green off. For this we will set, if I do, set B P 3.2. So this will make green off. Once we will perform these set of operation, then we will transfer the sequence of the program to a delay subroutine. so that controller should execute few instructions for the delay. So here I will write instructions. I will call delay. Right. Somewhere I will write the delay routine at the address at the org 0100h. Here I will write delay. Right. So for simple instructions I will write here move r0 comma hash. Suppose here I write 0fh and d, j and z r0 come to label b1. b1 is this and otherwise go to ready. So now with this controller will come here, it will execute this set of instruction. So some delay will be generated, then with the return it will come back to the main program. And once we are in the main program, again I will write here RET. With this RET, what will happen? It will go to this subroutine. Because see, with this alcohol, the sequence of program will come to, they will compare. It will compare, it will come here. It will execute this set of instruction. Here again there is one alcohol. With this alcohol, it will come to this subroutine. And in the last there is RET. With this RET, it will come to this place. Again here RET is written, from here it will come back to main program. So in this way. Now, if the room temperature and reference temperature are not equal, then when this instruction will be executed, at that point of time, it will go to label further check. It will come here. And here I have written instruction jump no carry. Jump no carry means A is greater than A. A means room temperature. Room temperature which is in A, whose value in A is greater than reference temperature. This is the condition, jump no carry. Right? Then go to, if this is the condition, then this indicates that if no carry, in this case, if the room temperature is greater than reference temperature, then carry flag will remain 0. Then jump no carry instruction will transfer the sequence of our program to the label which we will write. So we will write the label. If this is the condition, then what we have to do? Room temperature is greater than reference temperature. Room temperature is greater than reference temperature, then we have to on red LED. So I will write the label here, JNC on underscore red, right? On underscore red. So on underscore red, I will write this label here, on underscore red, right? So sequence of program will come to this label when carry is not generated. And if carry is generated, this means room temperature is less than reference temperature. Because when this instruction is executed, CJNE, then A minus 0F, this operation will be performed. In A we have room temperature, and this is reference temperature. So if A is less than 0F, room temperature is less than reference temperature, then carry will be generated. So if that is the case, so if carry is generated, then due to this instruction, sequence of program will not go to the label on RED. It will remain here and execute these set of instructions. So these set of instructions, I will write the comment here, when room temperature, that is the value of A, is less than reference temperature, right? And here when the room temperature is greater than the reference temperature. So if room temperature is less than reference temperature, then what we have to do? Room temperature is less than reference temperature, then on green LED. Green LED, this has to be on and remaining two are off. So we write the instruction to off set B P 3.0 of green, of red. Okay. Then set B P 3.1 of yellow. Then CLR P 3.2 on green. Then I'll call delay and RE. After this, here we will write the instruction to make our red LED on. So for this, red LED is 3.0. So write the instruction CLR P 3.0 red on. Then set B P 3.1 and this means yellow off, and set B P 3.2 means green off, and alcohol delay and RET. And finally here you write end. So this instruction you write after this. Delay is the routine right after this. So in this way, these set of instructions will perform this particular operation.